Yo, what's good, guys? Today we're going to be going over the direct comparison test. So direct comparison test is used to determine like a series, sort of like n to the fourth minus and then some value over like n to the fifth plus or minus, plus or minus up here. It doesn't matter if it's being plus or minus or added or subtracted. Um, and then you basically want to determine a b sub n from your highest and like parts of your function that grow the fastest. So let's say that I had like cosine x here or something like this, and I had like sine x here. These don't grow as fast as these. So essentially, what your test series would be is just 1 over n, because you basically take a limit at infinity and figure out what is the simplest form it can be in. And if you take a limit at infinity of this, it's just 1 over n. It's the same idea. So it's like exactly the same, minus these cosines and sine that don't even affect the problem at the highest level, at higher ends. I guess it should be cosine and sine n. My bad. So these are just some like conditions that you have to meet in order to use this test, but they're not even conditions for the most part. B sub n has to be greater than 0 for all n is true. So you can't use an alternating series, and you can't use like negative 1 over n and then have it be like that. This is not correct because this is always negative. So yes, this is true always, but you will rarely ever run into a problem where you even have a chance to make something negative. I mean, I'm sure that you could like always add an alternating series, but like, or alternating part of it, but it's like if you add an alternating like negative 1 to the nth power times like 1 over n, um well, I guess in this 1 over like n squared, this doesn't affect this at all, really. um, you could do without this and just have this and compare it to this. The alternating series aspect of it doesn't really change the whether or not something's convergent or divergent, except in certain cases. So just know, don't use alternating series. Don't use negative 1 to the nth, aka an alternating series. And this a sub n has to be less than b sub n. This is kind of deceitful, because it's true, but it's also not true, because you'll see later on as we do more problems that this isn't true for all n. It's true for all of n past a certain point in a lot of cases. Sometimes it's true for all n. Sometimes it's absolutely true for all n. Sometimes it's not true for all n though. Like, here's an example where it's true for all n plus 1 and then 1 over n. This is always bigger than this. If I put 2 here, this is 1/3 and this is 1/2. This is bigger. If I put 1 here, this is 1/2 and this is 1. This is always true. But if I put n minus 1 and then I used 1 over n, it's vice versa. This is always bigger than this. So if you have this, you don't want to use this, because this is always bigger. There's no n value where this is not bigger than this. So I mean, if you got this, if you got the series of this, you probably wouldn't even do direct comparison. So you wouldn't use this. Typically, direct comparison is like you have to have n value, like n to some exponent on top and bottom, is when you usually use it, like in this instance. So you'll see later on, but like there are certain points where like n is greater, or b sub n is greater than a sub n for all n past 15 or something like that, or past 30, or even it can go as far as 1 million. So the thing about direct comparison, and why this is true, is because, okay, if you cut out the first, I don't know, 1,000 terms of a series, you know, and say that series is convergent, is that series still convergent if you cut out those first 1,000? Yeah, it's so convergent. The value at which it converges to is different, but the idea of it being convergent and divergent is it's still the same. Because it's the same series, it just starts at a different point, or starts at a different end value. So it's still convergent or divergent. It just changes the value at which it converges and diverges. And that's not what that's not what the direct comparison test cares about. It doesn't care about what values it converges at. It just cares about whether or not it does or doesn't. So basically, if you get something like this or this, it doesn't matter. Don't even worry about this. Just say that it's true for all n. Um, because the first like x amount of terms don't matter at all. Um, so yeah, I get that that's like a little confusing, but you'll see when we do problems that why exactly that kind of works. So here is the here are the sort of like things, the assumption or conditions that you have to meet to be convergent or divergent. I know that these are conditions. These are like more assumptions than conditions. If B sub n is convergent, and so is A sub n. So if your test comparison, if your comparison series is convergent, then so is the series that you actually care about, A sub n. If A sub n, the series that you care about, is divergent, then so is B sub n. So you'll see how both of these kind of work and how you determine whether or not one is divergent or not. There is a little bit of leeway with this second one. I'll just say that. Um, if your B sub n is larger than your A sub n, there is some funky stuff where you can infer that it's divergent. So yeah, I think that the last problem that we do deals with that. Okay, let's get started. So looking at this, you should be able to tell, or well, maybe not because you're watching this video, but um, this your B sub n. So 5 and 9, obviously, no matter what value of n they are, they're not going to grow. Um, they're constant. So these right here are your values that are going to grow based on what n is, obviously. So you essentially want to take a limit at infinity and then figure out what these are equal to. What this sort of equals to. So this equals to 1 over n squared. This is your b sub n. Um, your test statistic lol. Your test series is just gonna be your a simplified form of your fastest growing parts of your function. Um, basically just over each other. Like if this was n to the fifth over n to the sixth, this would just be 1 over n. Um, so just think like you're taking a limit at infinity, and then sort of like subtract your exponents. That's really how you do these, is you subtract your exponents and find this. Okay, well, 1 over n squared is convergent. So looking back up at our things, looking back up at our conditions for being convergent and divergent, if B sub n is convergent, then so is A sub n. So this is our B sub n. This was the series that we made up to compare to this. Because it's as n grows towards infinity, this is what it'll model after. Um, I don't know if you can like maybe graph these somehow, but if you graph the sums or something like that, or you made a scatter plot of like sums of um, these, as your n got really, really, really big, it would look almost exactly like this. Because this is a limit at infinity, these are the same thing. These equal the same thing. So this thing, because our B sub n is convergent, and according to our thing, according to direct comparison, this is also convergent. So this entire thing is convergent because B sub n is also, because this is an identity. You could also do p series test, If you didn't know, you could do p-series test on it and figure out if it's convergent or divergent. So yeah, this is convergent. Um, I don't know if I have if I have B sub n as a harmonic series somewhere in here, but you should know that 1 over n is divergent. That's an identity. That's yeah. 1 over n is always divergent no matter what. That is how these two, 1 over n squared and 1 over n, are going to be your most important sort of identities for doing these. Okay, ln of ln of n over n. Okay, this is harmonic series. So ln of n, as a limit and as it approaches infinity, ln of n grows slower than n. That's just that's just true, because if you just think about what ln actually is, it's saying that e to some value that is what ln of n equals. So let's say that's x equals n. So if you think about just how this works, this 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 has to be lower than, or this x value is essentially what ln of n equals in this instance. If you think about it, if you can follow what I'm saying. I know I'm being a little bit kind of, you know, whatever. I'm not explaining this as well as I think I should be. Um, so this is essentially what ln of n equals. Like that's just, you know, that's what we learned in algebra 2. This is how logarithms and ln's work. So x compared to n is always going to be smaller than n. So say that this is like, I don't know, e to the fifth. Not okay. It's not always. It's gonna be smaller at some points. We'll talk about that at the end of this problem. Say that this is like e to the fifth, or that this is like e to the x. My bad. Say this is e to the x equals 5. We want to figure out what our x value, what our x value is essentially going to be what ln is. So you know we take ln of it, and then we get or we take ln of both sides, we get ln of 5 equals x. So ln of 5 is smaller than 5, because it has to be. I don't know what it is off the top of my head, obviously, but it has to be smaller than 5. That's just how ln's work. That's how every single thing about logs works. So we should know that this is growing, that the top is growing slower than the bottom. So b sub n is going to equal 1 over n, because the limit on infinity of this, since bottom is growing faster than top, our top doesn't matter, and our bottom is what matters. So this is 1 over n. This is divergent. I cannot stress this enough. This is divergent. So because this is divergent and it is greater, it is or it's smaller than let me check. Yeah, because ln of n is greater than 1 over n for all values except let me think. Ln of 3 over 3 and then 1 over 3. Yeah. So this is one of the only times that it's not. 3 is your cutoff point, actually. So for all values greater than 3, greater than or equal to 3, I think. Yeah, greater than or equal to 3, uh, this is smaller than this. This function right here is bigger than this for all values greater than or equal to 3 of n. So this is essentially like this is essentially the idea that you can bypass the first couple terms if in the long haul it is bigger. Since 3 constitutes the first couple of, well, anything constitutes the first couple of ends or first couple of terms, but like since we can tell that this is a really small number and is not going to affect the long-term uh, uh, convergence of the thing of the function of the series, then we can say that, yeah, for all n, we can just assume that it's all n. So yeah, I don't feel like I'm explaining this as well as I should be, but that's because mostly all the n's from 3 to infinity are greater, where is a sub n is greater than b sub n, then we can ignore the first, what, 4 or 3, um 0, 1, 2 n. So yes, so ln of n over n is divergent because it's greater than our b sub n, and our b sub n is divergent. Okay, here we are with the probably the hardest problem that I've ever seen for this, for direct comparison. Okay, so your first instinct should be to say, okay, these right here are constant. So b sub n, and this is our growing part. So b sub n should equal 1 over n to the 1/2. Okay, so this makes sense. This makes sense so far. This is divergent because of p-series tests. However, though, there's one small problem with this that we touched on in this problem as well. 1 over 10 plus n to the 1/2 is less than 1 over n to the 1/2. This 10 makes it so that the denominator is always bigger than this denominator, this 10 plus. So this is always going to be smaller than this. So what this means is that we can't use this b sub n. Okay, so from this point you might get like a little bit confused. I'm like, hey, what? Okay, so we can't use this. Well, I don't see any other limit at infinity that would model this sort of thing. Well, essentially what you want to do is you just want to pick something that also diverges and is greater than your series, or greater than this series. Or I mean, not greater than, or is less than your series. So what we can do is we can just pick 1 over n because this diverges. And it's less than 1 over 10 plus n to the 1/2. This is greater than this. For all, okay, so now we're gonna employ the trick that we used up here where n had to be, where we can skip the first couple terms. This is true. Looking at my notes, this is just true for all n is greater than or equal to 14. So for example, 15, this is greater than this. 1 over 15 is less than whatever this square root of 15 plus 10. So yeah. So since this series is greater than, since our main series, our a sub n is greater than b sub n, and b sub n diverges, this series also diverges. Alright. I hope you find that helpful. This series is really this test is really kind of a mess to like sort of like explain, just because it's really it just takes like a different way of thinking, I think. I don't think that you really have ever anybody. I think that this would be like the first time that you would think sort of in this aspect, of finding using limits to basically evaluate a series, and um, use a limit to sort of approximate